For the UGC lecture series on laser physics and the Swayam portal. I have been explaining the importance of laser in modern science and technology for a long time, and I explained what are the differences between a laser light and ordinary light. Then we saw some basic equations and essential concepts to understand the behavior of laser, and then we went on to explain a few most commonly used lasers. Already I have given examples of some solid state laser, semiconductor solid state laser, glass type solid state laser, which means insulated solid state laser, liquid laser, and few examples of gas lasers. There are few more examples like a free electron laser where the electron is in a plasma. This free electron laser most of the countries do not have because it is rather expensive. It is meant for certain other purpose, but it is a very ingenious idea in fact. What is commonly available throughout India in universities, colleges, where teaching is more important, those lasers already I have covered, but I want to go in detail at least one laser with the full engineering detail, design detail. Now this particular, the best example I could think of is a helium neon laser, because until about 10 or 15 years ago, when semiconductor lasers were not so popular, they were not so efficient, they had their own limitations. Helium neon laser was the most commonly available laser in many postgraduate and undergraduate physics laboratories or engineering colleges also, because helium neon laser is a compact one which can give a continuous wave laser of about 1 milliwatt to maximum 50 milliwatt. 1 milliwatt will be of this size, this length, 50 milliwatt will be this one, that is a size. Even 50 milliwatt was rather expensive. Most common is 2 milliwatt laser. Many universities, college had it. I want to they are still valuable. I want to explain the design details so that people will appreciate how a laser is made at all, what are the constriction, what are the limitations, how to overcome, how to design a very fine laser. With that in mind, let us go into the detail. As I mentioned, it was the first successful gas laser and it is most commonly used even now. What we do in designing this, first we take a long tube. It will be a glass tube, very good quality glass tube. Length will be about a meter and the diameter about 4 millimeter. Then connect it to a vacuum pump, a rotary pump plus a diffusion pump put together, running for days together, will be able to completely remove the air inside and occluded gases, occluded impurities, everything inside the glass walls. All this will be removed. That is the first step. Then fill it with helium and neon gases. These are easily available. Pure helium and neon gases are easily available in the market because they are the ones used in the advertisement. Wherever you go, if you see the pink color, pink advertisement light, that will be helium or neon. Both are very similar. People use mostly neon. That kind of gases you can take in. The helium, some of you may be familiar with the helium because even the children know. Do you know why? It is like this. If you go to the beaches or some exhibitions, the children will get a balloon of very big size in which helium is filled. Helium is a very light gas. perhaps the lightest gas. If you just hold the balloon, let it go, it will keep on going because it's very light. It will just start flowing up, floating up in there and keep on going, and you will lose it. Most often you will lose it unless you have a tail to hold it back, it will escape. That's a property of a helium balloon. Sometimes they make the balloon a bit heavy, and then when they fill the helium gas, it will not run away. You can hold it still and you can easily catch and play around. That's a very common gas, helium. Neon, as I told you, it is a gas used in the discharge lamp for the advertisement. Now, these two gases should be filled in the ratio of 7:1 at a total pressure of about 1 torr. In a plasma tube of about 100 centimeter long and 4 millimeter diameter. That's the first thing. Then at the two end, you must have an electrode inserted. One will be a positive electrode, other will be a negative electrode. Under that condition, you connect this electrode to a high voltage of about 2000 volts. 1000 volts or 2000 volts, somewhere on this range. It depends on the length, it depends on so many other parameters. Let us say 2000 volts. Then, once you switch on this one, a discharge will be struck in the plasma tube. Discharge means you have plenty of ions. Ions means you have plenty of electrons, helium ion, neon ion, and whatever other gas impurity are there, many kind of ions will be there present. Electron from one end, let us say this is the negative electrode, cathode, electron will run towards the anode because there is a potential difference of about, the voltage applied is about 2000 volts, so you will have a rush of this electron. This electron will hit on the walls, will hit on helium, will hit on neon. Both gases will get hit. Remember, both of them are rare gases. They are very tiny. They will get hit by the electrons. Then both gases will get excited. This is the energy level of helium on the left side, neon on the right side. All these energy levels are given by spectroscopists, 1, 1s, 2, 3s, 2, 1s. These are the spectral notation. Unless you have studied about spectroscopy, you may not be able to understand what is the significance of this one. What is important for us is, these are the atomic energy levels of helium gas. In a similar fashion, on the other side, you have neon gas. This has the energy level, both blue or ground state energy level. The ground state energy level of neon is given certain number, 1s2, 2s2, 2p6, etc. Then slightly up, at a higher energy level, you have a 3s level. Above that, you have a 3p level. On the left side, you have a 4s level, 5s level. Like that, there are so many energy levels. Why sometimes some of them are called the S level, some of them are called P level, I am not going to describe. That is mostly in atomic spectroscopy you should have studied. Now, what is important for us is, if you excite helium by electrical discharge from 1s to 2s, there are two energy levels very closely related, closely separated. The helium atom will get excited there. Then the transition of helium atom from 2s level to 1s level is forbidden. Is not allowed, because the change in L, it will be just 0. Such transitions are not allowed, or they will not produce radiation. That's the meaning of this one. That means the helium has gone to a metastable state. Helium has gone to metastable state means it will be in excited state, but running around here and there. It will be something like an angry atom. It will be hitting everything. It will be hitting the walls of the tube, hitting the other helium atom, it will be hitting other neon atom, everything it will do. It is something sometime maybe you will see in your home. Suppose you just give a slap to your brother. He cannot, I mean younger brother, he cannot fight with you. So what he will do? He will be angry. He will go here and there and then hit the wall or hit the table or throw the book like that. He will show his anger in that way. In a similar fashion, helium is in the excited state. It will hit neon atom. The neon atom will be just hit and raised to the energy level of 5s and 2s. There are very closely related levels. These two levels can be easily reached by excited metastable state helium atom. Now look at it. If you forget the purpose of helium beyond this one. This particular transition is called a resonant energy transfer. What we mean by is the energy level separation between 1s and 2s levels of helium is very similar, almost equal to the energy level of neon between the ground state and the s level states. Because of this one, there is a resonance energy transfer. Now neon is in the excited state. Neon can transfer its energy radiatively to lower levels, 3p levels. It can produce spontaneous emission and also stimulated emission for 3 transition. Remember, 3 transition. One is 3391 nanometer, another one is 1152 nanometer, the third one is 632.8 nanometer. These are the 3 transitions possible. Out of this 3391, 1152 nanometer are infrared wave. Infrared, I mean, they can produce laser at these wavelengths also. They can produce another laser at 632.8 nanometer also. Now, this 633 nanometer, let us say forget that point here, let us say this 633 nanometer, let us say forget that point here, let us say 633 nanometer is a very beautiful red light. This is what you see. This is what we want. Then you will see there will be a competition between the 3 laser lines, because all the 3 laser lines are allowed transition. Allowed transition, why they are allowed? Now look at it. The neon is in the excited states of 5s or 4s energy level, and the transition is going to 3p level. In this case, change in the angular momentum is 1, minus 1. Since it is a minus 1, it is an allowed transition. When you say it is an allowed transition, you will be able to get a substantial quantity of radiative emission, or the emission is strong. That is the meaning of this one. In this case, look at carefully, there are all the 3 transitions are allowed, all of them are competing each other. Now what do we do? How do we get only red? This is where engineering detail come. Before that, whatever I said all this time, I have put in a simple formula to take a look at it. This I have already explained, I have just skipped. Out of this, only one point is very important. The transition moments line with lifetime of the upper laser level. 1 minute. What is upper laser level? In this case, 5s, 4s levels are upper laser level. 3p is a lower laser level. The 2s of helium is the pump level. So, we have now 3 levels. Now, look at it. Helium 2s level is a pump level. Neon 5s4 levels are upper laser level, and 3p is the lower laser level, because that is where laser transition stop. Below that there is another energy level also, 3s. This is not a lower laser level, this is some intermediate level. Okay. So, the transition from 3p to 3s also is allowed. You will get some radiation, but we are not going to consider this one. What is important of 3s level we will see later. Right now we are interested only this: pump level, upper laser level, lower laser level, and the ground lead, which are shown by the blue light. Blue color represents the ground state of neon. That means we have now got a 4 level laser scheme which is capable of producing continuous wave laser. Next step is how to make a continuous wave laser emission very effective, very efficient. That's something we have to see the engineering detail. That's first thing. Secondly, how to avoid other 2 lines. See, you have to avoid 3391 as much as 1152 nanometer. These 2 infrared laser lines should be somehow or other kicked out, because we don't want them. Now, this is where the engineering details come into the picture. Okay, the first thing, the first and the most important thing is make the diameter of the tube very small, of the order of 4 millimeter or 3 millimeter. Why? If we have narrow tube, then atom which have gone to 3p level will get will get hit by helium atom, other neon atom, and also in the surface of the wall. When it hits the surface of the wall, it will lose its energy, and then from there it will easily go to 3s level. Once it goes to 3s level, what is the advantage? The lower laser level will be practically empty. Let us say it is 0. If only 10 atoms are there in 3p level and 100 atoms are there in 5s level, then population inversion is very high, because population inversion is the difference between upper population in the upper laser level, lower laser level. In our example, 5s level there are 10 atoms, angry atoms. At 3p level you have not so angry but lower energy level atom. They are only 1 or 2, let us say 1. Then the population difference is 10 minus 1, 9. So, because of the energy that is given out by stimulated emission is proportional to the population inversion density, you will be able to get a laser action very easily. To improve the optical gain for this kind of laser is rather low, because the discharge is there are so many other difficulties. The discharge is not so strong, and you cannot increase the discharge beyond level, because the whole tube will heat it up, then laser action can stop. Because of this one, throughout in a gas laser, particularly helium ion laser and argon ion laser, helium ion laser 5 milliwatt, 10 milliwatt, 50 milliwatt, water circulation may be required, or air flow will be there. Continuous air flow will be circulated inside, so that the whole tube is cool. In argon laser, that air cooling is not sufficient. You need very good water cooling. In this kind of helium neon laser, air cooling is okay. Because of all these limitations, the power that comes out will be only about 1 milliwatt, 10 milliwatt maximum. If you have a long length instead of half meter, 1 meter, 5 meter, you can have maximum of about 50 milliwatt helium neon laser. Next point to be considered is this one. In all this, we have said that 3391 and 119252, these are the infrared laser. The 633 is a red laser. How to kick out, avoid other two laser transition is a most important design aspect. For that, what we do, we will have two mirrors. One mirror will have a reflectivity of 100% only for red. Another mirror will have reflectivity of 95% only for red. For all other wavelength, it will not have a reflectivity beyond 30% or 40%. How to do that one? To do that only, you need specialized laser mirrors which have lambda 2 stacks, half lambda stacks. That is, you prepare a thin film coating of two types of material, low refractive index and high refractive index, each of thickness lambda by 2. If you give that kind of design one after another, that kind of mirror will have a specific reflection of 99% or even 100% at 633 nanometer. Whenever I say lambda, that lambda is 633 nanometer. That means the reflective coating, half lambda stacks, are exclusive for 633 nanometer and not for other two. That means you are deliberately avoiding any kind of feedback for the two infrared laser lines. Once you have avoided, whatever power is available due to population inversion at 5s and 3p level, whatever is a photon available inside, they will be specifically, selectively privileged. They will give a privileged interaction to produce laser action at 633 nanometer. That is the first step. In a few lectures before, I told you how a number of axial modes are sustained. Out of that, how only few modes will undergo break into oscillation. They will get into laser line. All those already explained. Here there is only one subtle point which I want to bring to your mind. This 3391 nanometer is capable of producing amplified spontaneous emission, which already I have explained long ago, some 4 or 5 lectures ago, or at the beginning or at the theoretical point. I have explained what is a amplified spontaneous emission. Now let us come back. This particular 3391 nanometer infrared laser line has such a high gain that even by a single transit, it is capable of producing laser action. Now look at this one. Even by a single transit, it is capable of producing laser action, means you cannot suppress it putting one mirror or another mirror. I give an example, very good example. You will never forget it. Suppose I have a competition, a running competition. In a school, there are very smart boys who will just run even some 3 times, 4 times a day, and after that they will be able to win the race. And there are other people who needs regular training 100 times before they go for the competition. The amplified spontaneous emission at 3391 is capable of producing laser action even in a one single transit. So to avoid this, what do? You specifically say he has got some problem, or he is stronger than, or he has got an age greater, much greater than 633 nanometer. So you don't allow him to go for a running competition at all. You have kind of prejudice, and you want to avoid this particular laser at 3391 nanometer. You don't allow him to come into the competition, because if he comes to the competition, he will win it. So what do? Very clever idea has been done. You apply a magnetic field all along the helium-ion laser tube, and then the magnetic field will produce an expansion, or it will just broaden the line width of 33 nanometer. When it broadens, when it's going to be a big bandwidth, it will lose the gain. The gain is inversely proportional to the bandwidth of any radiation. By this way, the optical gain of infrared laser is deliberately suppressed. Only by this you will be able to produce laser at 633 nanometer, which we want. So if you open any other commercially available laser, or if you go with a magnet in your pocket, if you have any magnetic material ion near the discharge tube, just if you go, just run this one, you will see, if you have a magnetometer, you will see the magnetometer will just show a reflection, deflection, saying or indicating that there is a magnetic field or magnetic material or provided throughout the discharge channel. That is the only way you can avoid any kind of laser action from the infrared and prefer 633, which is the most commonly used laser. Only one more point I want to say. Since this is a very handy laser, and since you have used very good quality mirrors, the purity of the laser is very high. The spectral width that comes out from the laser is about 0.1 nanometer or even less. Such a single mode or a very pure laser are very much required for holography or anything related to the interference. See, the interference, the fringes contrast will be very good for a single wavelength. That is why we say laser is essential for, laser is very important for observing interference pattern. Or the other way, if you say laser, you can see the interference pattern with the good contrast. It is something like a TV with the large number of pixels, then the contrast of the face will be very good, it will be more realistic. In a similar fashion, in this 633, you have extreme purity. Because of this one, this particular laser is best for holographic construction, reconstruction. Earlier, I told you once that semiconductor laser is made for each other for optical communication, or I would say optical communication is best with the semiconductor laser. Semiconductor laser is the best use for optical communication. They are made for each other. In a similar fashion, holography means He-Ne laser. He-Ne laser means holography. The He-Ne laser does not have any other big applications. I have given the essential feature of not only helium-ion laser, how the design is made to get a particular type of laser during any kind of market production. Thank you very much.